Okay, in this lesson we are going to be looking at what are called linear programming problems, which are problems where it's a whole situation and people are given some different constraints, some different restrictions that are placed on them, and then they want to either make the most profit possible or minimize the most expenses or something like that. And so what you are going to do, just the general process, is you're going to, first of all, define your variables, and then you're going to write a system of inequalities that address all the restrictions that are in the problem, and then you'll go ahead and graph those. And then from that point on, it'll be very similar to what we did yesterday, where you're going to graph your inequalities. You're going to look for a feasible region where you see all of the colors, and then you'll look for the corners of that feasible region and plug them into a function that you will write in order to either maximize or minimize whatever you're trying to find. So that's sort of the general process that we are going to use when we do these problems. And we're going to do two of them together. Typically, the hardest part to these is to be able to write your equations. And once you have your equations written, people typically don't have too much trouble. Okay, so in this problem, we have a vet, Bryn, and she has a receptionist schedule appointments for her. She allows 40 minutes for a surgery and 20 minutes for a routine office visit. And now here's some restrictions. Bryn can't do more than 6 surgeries in a day, and she only has 420 minutes or 7 hours to be available for appointments. And then she's got some costs, some money that she's trying to make. An office visit costs $55, and most surgeries cost $125. And you want to find a combination of office visits and surgeries that maximizes Bryn's profit per day. Okay? So the first thing you need to do is you need to kind of define some variables. So you need to think about what's changing for her. And the things that are changing for Bryn would be how many office visits she does and how many surgeries she does in a day. All right? So we're going to call X the number of surgeries. I'm just going to define that. And you always have to define your variables, okay? Surgeries. And we'll do Y the number of office visits. And if you wanted to use different letters, that's totally fine. I just like to stick to those because it helps us be able to graph them. All right. Then we're going to come up with some restrictions that will happen every time we do this, okay? I will tell you, first of all, there's two things that almost always, when you do a linear programming problem, two inequalities that you're going to write almost every time. One of them would be X is greater than or equal to 0. Typically, no matter what X stands for, you can't have a negative number of it. So in this case, X is surgeries. I can't have a negative number of surgeries, so when I know my surgeries have to be, I can do 0 surgeries, that's okay, but I can't, and I can do more surgeries than that, but I certainly can't do any less. And same thing with office visits in this case, they have to be greater than or equal to 0. I can't have a negative number of office visits, and I will tell you those two inequalities will be written in 99.9% of every one of these linear programming problems that you're going to do. So on a quiz or a test, everybody should at least be able to get those two in there, okay? Then we're going to kind of read through what happens here. So we've got one equation that we need to write about how much time she has, okay? And if we look at how much time she has, what I can see is that it's 40 minutes for every surgery that she does. Well, I don't know how many surgeries she's going to do. We called the surgeries X, so it would be 40 minutes for every X surgeries that she does, and 20 minutes for the office visits. Okay, office visits are Y, and then she has 420 minutes total in a day to work. Okay, so what that will look like is that will look like this. 40x plus 20y, so 40 minutes for every surgery, 20 minutes for every office visit. All of that put together better be less than 420 minutes because that's all she has to work. Okay, and then it also says that she can't do more than 6 surgeries in a day. So her surgeries, which we called X, has to be less than or equal to 6. Okay, the money piece of it, we won't worry right now. The money piece is going to come in when that's what we're trying to maximize or minimize. So yesterday when we did your homework and our notes together and you were saying, where do we get this function from? This is where you're going to get that function, and we will talk about the money piece of it in a minute, okay? So now we've got 4 equations that we need to graph. And just to clear this up a little bit, you guys, these 2 equations here, the x is greater than 0 and y is greater than 0, what happens, here's x is greater than 0, and you would shade to the right. Here's y is greater than 0, and you would shade up. All that does is it limits your graph to the upper right-hand quadrant. And so I am not going to take the time to graph those on here just because it gets to be such a mess. And so if you don't want to graph them either, that's fine. I will assume that you know that that limits your graph to the upper right-hand quadrant, and we're going to be cool with that, okay? So then the next equation, this one right here, is not in y equals mx plus b form right now. So I am going to go ahead and get it there. I'm actually going to move this equation over here for a minute. I will get that into y equals mx plus b form. So we want to subtract our 40x so that we have 20y is less than or equal to negative 40x plus 420. And then divide by 20. And y would be less than or equal to negative 2x plus 21. Okay, so now we are going to go ahead and plot that, and unfortunately it's not coming out to be super duper duper pretty, but here we go. My y-intercept is 21, which is going to be right about there. Okay, my slope is negative 2. Now, negative 2, really if you're at 21 and you have a slope of negative 2, you should go down 2 and put you at 19 and right 1, which would put you at 1. I want you to notice how my axes are scaled. They're scaled by 4s on the y-axis, and they're also scaled by 4s on the x-axis. And as long as those axes are scaled the same way, you can use the rule where you go down 2 boxes and write 1 box because it's proportional. If that wasn't the case, if they weren't scaled the same, then you would actually have to count. So I am going to go down 2 boxes and write 1, and down 2 and write 1, and down 2 and write 1, and I would connect these. Now I don't need to connect anything beyond the first quadrant because that doesn't matter. So I'm going to go from there down to here, okay? And it is a less than symbol, so I would shade underneath it. Notice I'm only sticking to the upper right-hand quadrant. I didn't graph those x's greater than or equal to 0 and y is greater than or equal to 0, but it's implied to mean that. Okay, and then I have this other equation right here, which is x is less than 6. If it's an x only in the equation, that means you have a vertical line, and so you have a vertical line at 6, which is right here. Okay, and then I would have to shade less than that, which would be over here. All right, and then your feasible region would be only the spots where you see both colors. So it would be in here where you see both colors. Always only in the first quadrant when you do this. Okay, so here we go. Now we can see that we have 4 corners to this feasible region. One of them is right here at 0, 0. One of them is at 6, 0. One of them is up here at 0, 21. And this one isn't quite so pretty. I can't exactly figure out what it is. So that means I need to do a little solving, okay? So that equation is where the green and the red line intersect. So the green line, just kind of off to the side, I'm going to pretend this is equals. The green line was negative 2x plus 21. And the red line was x equals 6. So I already know that my x coordinate is 6, basically. If I go ahead and plug that in right there, then I have negative 2 times 6, which is 12, negative 12, plus 21 gives me 9. Okay, so this coordinate right there is at 6, 9. Okay, so those are my corners of my feasible region. I'm going to go ahead and just list those in my table down here so that I can keep track of my information neatly. Okay, again, those came from the 4 corners. Now, what we're missing here is we're missing a function right here. We are trying to either maximize or minimize something. And so if we maximize this, what I'm trying to maximize is her profit, okay? And she gets $55 for every office visit, and she gets $125 for every surgery. So what that would look like is this. I'm just going to put f of x, y. She gets $125 for every surgery, and she gets $55 for every office visit. So that's where your equations are going to come, okay? And then what you do is, again, you plug this information just like we did yesterday, the coordinates into the equation. So here I would do 125 times 0 plus 55 times 21. And when I do that, I get 1,155, okay? Now, I know you can plug these all in, so I'll just do one more. 125 times 6 plus 55 times 9. When I simplify that, I get 1,245. Okay, and I'm just going to tell you that you get 0 here and you get 750 here. Okay, so Bryn in this case was trying to make the most money possible. So that's what I care about, is when she can make the most money. So here's where she can make the most money. And what I need you to do is be able to put that answer in context, okay? So this is what I want you to write. I want you to write a sentence that goes something like this. Excuse me. Bryn will make a max profit of $1,245 when she does, okay, and here's the coordinate that goes along with that. So your x is 6 and your 6 is surgeries, and your y is 9 and your y is office visits. So when she does 6 surgeries and 9 office visits. And he wants you to write a sentence like that so that everything is in context and you know exactly what this whole problem solved, okay? And so that is that one right there. All right, we are going to do one more problem here. I know these are long, so thanks for hanging in there with me. The next one is about Ethan, who owns a landscape company. He has a crew that mows lawn and prunes shrubbery. The company schedules 1 hour for mowing jobs and 3 hours for pruning jobs, and each crew is scheduled for no more than 2 pruning jobs a day. Each crew's schedule is set up for a maximum of 9 hours per day. On the average, they charge for mowing is $40 and for pruning is $120. Find a combination of mowing lawns and pruning shrubs that will maximize the income Ethan's company receives. Again, in this case, I'm trying to maximize. Sometimes you'll try to minimize, just so you know, but most of the time you'll try to maximize. Okay, so the first thing you need to know, again, is to be able to define the variables. And so you have 2 things going on here. You have mowing and you have pruning, okay? So we're going to say X is the number of mowing jobs and Y is the number of pruning jobs. All right, so again, you guys, you should have these 2 inequalities pretty much every time. X is greater than 0 and Y is greater than or equal to 0. Can't have negative number of mowing jobs or negative number of pruning jobs. Okay, what that does again is just limits us to the upper right hand quadrant, which I'm not going to take the time to graph those because it gets so messy up here. All right, so then we need to kind of listen to our restrictions. It says the company schedules 1 hour for mowing jobs and 3 hours for pruning jobs. So let's talk about this. 1 hour for every job I do mowing, 3 hours for every job I do where I prune, and they can only work a maximum of 9 hours per day. Okay, so what that will look like is this: 1 hour for every mowing job, and 2 hours, 3 hours for every pruning job. And when I add my mowing jobs and my pruning jobs, it can't be any more than 9 hours. Okay? And then the other thing it says is that they can do no more than 2 pruning jobs a day. Okay? No more than 2 pruning jobs a day, which means that your pruning jobs are your Y, so Y has to be less than or equal to 2. Okay? So I am going to, first of all, I'm going to ignore the ones that are in black and just know that it limits us to the upper right-hand quadrant. I'm going to go ahead and graph this equation first. It happens to be a horizontal line because it only has a Y in it. And so a horizontal line at 2 would look like this. And it has to be all the spots that are less than 2. So I'm going to shade below it. Notice I'm only shading in the upper right-hand quadrant. Okay? And then this other equation is not yet in y equals mx plus b form, so I'll go ahead and subtract x, and I will have 3y is less than or equal to negative x plus 9, divide by 3, and I will have y is less than or equal to negative 1/3 x plus 3. Okay, so here's that equation. So now I'll go ahead and graph that one. That one has a y-intercept of 3 and a slope of negative 1/3, which means I go down 1, right 3, down 1, right 3, and this is kind of running off the graph. I apologize for that. Down 1, right 3, way over there. Okay, and that is also a less than symbol, so I will shade below that. And I kind of ran off the graph here, but we need to darken in now the region where we see both the green, or both the blue and the red, which would be this region in here. All right, so we need to come up with the corners here. And we can see that this corner, obviously, is 0, 0. And this corner we can see is 0, 2. That's not a problem. This corner right here might not be real obvious, but it is basically where the red line hits the x-axis. And what I know at this spot, I don't know my x-coordinate, but I know that my y-coordinate is 0. So what I can do is I can go back up to this line right here, which is the red line, and plug in 0 for y. I'm just going to pretend it's equals instead. Okay, and your graph might work fine, but I'm just going to show you how to do this. I'll subtract 3, so I have negative 3 equals negative 1/3 x, and then I'll multiply by negative 3, and x would be 9. Okay, so that is the coordinate 9, 0. So now I'll go ahead and stick those coordinates into my function here. Oh, you know what? I have one more. Sorry. Right here, I didn't do this corner. Okay, and that would be the point 3, 2. Okay, all right. And now I'll list those here, those 4 corners that we just came up with. All right, and now we need a function right here. So we're trying to make, in this case, the most money that we can. And it says that they make $40 for every pruning job. Sorry, $40 for every lawn mowing job and $120 for every pruning job. So it would look something like this. $40 every time they do a mowing job, $120 every time they do a pruning job. Okay? So again, I'm not going to do every one of these, but you'll plug in your coordinates then. 40 times 0 plus 120 times 0 obviously will give you 0. Okay, and I'll just keep you, I'm not going to take the time to fill all those in, but I'll tell you that you get 360, 240, or 360. So in this case, I have a tie right here. These are both the max amount of money that I can make. So, and that's what I'm trying to do here. I'm trying to maximize my profit. So this is what I will say. Ethan will make a max profit of $360 when he schedules, oops, 3 mowing and 2 pruning jobs or 9 mowing and 0 pruning jobs. Whew. All right, we did it.